Okay, next up is RefCell, and actually today don't even need to use VS Code because there's basically no code here, but it's still interesting because the whole book is interesting. So RefCell, unlike a regular cell, a RefCell does allow you to borrow its contents at a small runtime cost. And the runtime part is interesting. If you look at RefCell, you can just look at it directly and you can see there's a lot of like a borrow flag. I'll show you borrow flag. So it's got this this thing called, you don't need to use this you don't need to know this to use a RefCell, but there's an example of the runtime cost it's talking about. So there's a flag and it checks to see if it's used or not, and if somebody's using it to write or to read, and then does all of that to track the borrows at runtime. And then if you have if you contravene the rules and you have like 2 mutable borrows, then instead of not compiling, it'll actually just panic at runtime. So that's the runtime thing. A RefCell does not only hold a T, but also holds a counter. That's what we just looked at, that keeps track of any outstanding borrows. If you try to borrow it while it's mutably borrowed, it will panic, which avoids undefined behavior. And just like a cell, it can only be used within a single thread, which is why the book doesn't really talk about RefCell, because it's all about threads. Borrowing the contents of a RefCell is done by calling borrow or borrow mute, and this is just the easiest example you can imagine. Borrow mute, and there's no other borrow, so you can just push in and modify vec directly. That's talking about this former example where if you have a regular cell, you have to take the content out and then you push to it and then you set it back. Whereas with a RefCell, you can just do this directly, so it's a little bit more convenient. So there you go. They can be very useful, but they become rather useless when we need to do something with multiple threads, and so on the book goes to the more interesting types. Next up is Mutex and RwLock, which is a read-write lock. An RwLock, reader-writer lock, is the concurrent version of RefCell. So it's basically a RefCell, but it's multiple threads. It holds a T, it tracks any outstanding borrows. However, unlike a RefCell, it does not panic on conflicting borrows. Instead, it blocks the current thread. So you have to watch out for that. You don't want to hang around waiting for the thread. There's a try write RwLock. So if you think there might be like some other variable using it, then you will want to use these try read and try write, so that you can just give a quick try, see if it's being used, and if not, then you don't hang around letting the thread just spin around forever. So it blocks the thread, and if it blocks it, you have to patiently wait your turn, and if the other ones never end, then your program never ends. So watch out for that. Borrowing the contents of an RwLock is called locking. By locking it, we temporarily block concurrent conflicting borrows, allowing us to borrow it without causing data races. And Mutex is very similar, except it's a little bit simpler. And what it does is it only allows exclusive borrows, and so they're pretty similar. And then it will go into detail later, or the author of the book will, rather. Atomics. Now this is where it starts to get interesting, because UnsafeCell is coming up in a second. So atomic types are actually just cells. They represent the concurrent version of a cell. So you've got if you have RefCell, and the concurrent version is read-write lock. If you have a cell, then the concurrent version of a cell is an atomic, except for, like a cell, they avoid undefined behavior by making us copy values in and out as a whole without letting us borrow the contents directly. However, unlike a cell, they cannot be of arbitrary size. And because of that, there's no atomic T. That you've got all these types in the atomic module. There are only specific types, such as atomic U32, atomic pointer. And if you go to the standard library and you type atomic, you can see all these types: atomic I8, atomic pointer, atomic bool, and so on and so forth. Which ones are available depends on the platform. Yeah, that's right. If you have like not all platforms even support atomic types if you have a really old computer. So So yeah, they require support from the processor. And yeah, I guess chapter 7, we'll look at that more. Because they're so limited in size, atomics often don't directly contain the information that needs to be shared between threads. Instead, they're often used as a tool to make it possible to share other, often bigger things between threads. When atomics are used to say something about other data, things can get surprisingly complicated. And I'm just reading this for the first time. Don't directly contain the information that needs to be shared between threads. Oh, right, because inside they're just a, I think this is about how like RefCell has a bunch of, RefCell has a bunch of, you know, runtime information, and whereas atomics are just, they just have a unsafe cell inside. Let's see, let's look at atomic bool. Because these, atomic bool. Because atomic, the I8s and so on, they use this macro to implement them because there's so many of them. And so you can't see. There you go. So I think that's what it's talking about. It's just an unsafe cell, so there's no other information. I think that's what it means. This I'm curious about. When atomics are used to say something about other data, things can get surprisingly complicated. So maybe get into that later. Unsafe cell. This is the fun part. An unsafe cell, which we just looked at here, is the primitive building block for interior mutability. And you actually see an unsafe cell everywhere. Like everything is just a wraparound unsafe cell. So an unsafe cell, T, wraps a T, but does not come with any conditions or restrictions to avoid undefined behavior, which is why it's called unsafe. So what it does is its get method just gives a raw pointer to the value it wraps, which can only be meaningfully used in unsafe blocks. Let's just look at that method. Unsafe cell. Go there and check out the get method. So there you go. There is the mutable pointer or raw pointer. Mutable raw pointer. Star mute. Sometimes people call it a star mute. And there you go. You always have to do like these casts to get to these raw pointers. You're like as const t as star const t as star mute t. And then that means, and just getting, the reason why this is not unsafe is because getting the pointer itself is not unsafe. It's the dereferencing it that's unsafe. So you get something that can potentially be unsafe, but just doing this is actually, you don't need an unsafe block. And so it leaves it up to the user or the authors of the standard library to use it in a way that does not cause any undefined behavior. Most commonly, an unsafe cell is not used directly, but wrapped in another type that provides safety through a limited interface, such as a cell or a mutex, and all types with interior mutability, including all types discussed above, are built on top of unsafe cell. So that's interesting. Whenever you go to anything with interior mutability, you're going to find unsafe cell. It's like that, always was meme, always has been. It's always unsafe cell. And if you go to like Mutex, then you look inside and you're going to find unsafe cell. And by the way, John Yangset did a really good video on that, on how like unsafe cell is used to do everything. So I'm sure it's easy for you to find. So there we go. And the next video will be, we'll get into this section here, send and sync. So see you then.